A 1979 Ford F100 is a pretty cool truck. Now, when you pair it with a classic engine swap of a 12-valve Cummins and a 5-speed, it's kind of even cooler. The motor and transmission, I believe, is from a first-gen Dodge with a second-gen transfer case, an NP241. It needs a couple things, like bodywork sanding, panels straightened, though also a few larger things like intercooler piping and an intercooler, as well as a good coat of paint. Unless you like the matte black look. But one thing I always wanted to see in this, which is quite common in swap vehicles, is a working speedometer. So how does the speedometer of the actual Ford F100 work? The Ford uses a cable that goes from the end of the transfer case, or in the case of it being a two-wheel drive, it goes on the end of the transmission, and it follows along the frame of the chassis all the way up to your dash, and it spins a magnet, and this magnet, essentially, as it's spinning faster and faster, it's turning the constant rotation into kind of a positional movement, if that makes any sense. Newer vehicles, like the Dodge, the powertrain was pulled from, utilize a device called a Hall effect sensor. It is mounted near the output of a transfer case or in a wheel hub, and usually its job is to send electrical pulses, kind of like a switch to a computer. The device can then determine how fast the vehicle is moving by using the time between pulses as well as physical relationships like gear ratios or tire sizes. When I first started this project, I didn't really know where to begin, so I kind of just started taking things apart. Now, I could buy extensions for the original Ford cable system and 3D print a mechanical adapter to go from Dodge output to Ford output. I also thought about using a motor to spin the magnet that I kind of mentioned before based on how fast the truck was moving, but that would also involve an Arduino. Then I found out that an Amazon servo, which I perfectly already have, fits perfectly in the middle of the Ford Speedo. So I started designing based around that. Which is now kind of where this mess is. So here is a 12 volt supply input, and it is going to a buck converter. So it'll step down the voltage to approximately 5 volts. This will supply power to the servo as well as to the Arduino. The Arduino is going to be doing all the thinking. It'll be taking in the pulses, doing the calculations, and then it knows how fast it's going. But how do you know how to show how fast it is? You can use a servo. Once you set it up, you'll set your 0 point, and you can make a plot of if pulses is this, speed is that, speed is then set to a specific angle. When I got the sensor, I actually had zero clue what it was going to give me. Is it a variable resistance? Is it going to give me a frequency? Is it 1, 0, blah, blah, blah. So you got to start somewhere. You got to test it. So I just spun it with a drill, measured it with a multimeter, and was getting some confusing values at first. Finally, after some trial and error, I was actually able to get a reasonable result. I was getting a slow frequency, and then I give it the beans.
She made fucking bang.
Then I got a higher frequency, so it seemed like it was working decently well. Next phase was trying to get it onto the actual Arduino itself. So all I did was just do a pull-up resistor on the Arduino and did a digital read every time, which is basically saying, is the sensor on that point on the gear or is it not? Progressing forward a little bit more, how often are those pulses coming in? That'll give you your frequency. I also ended up mapping the speed to a rough angle for the actual servo itself. And you kind of see it's a bit fluctuaty, though it seems to be quite accurate. At least the speed on the computer is actually matching the speed on the speedometer, though I don't know if the angular velocity of the sensor itself actually correlates to the correct speed shown on the speedometer. Basically what I'm trying to say is it's not calibrated. All right, well, then I think it's time to start throwing it in, right? Well, close. I got to redo the wiring a little bit nicer because I want it to be nice. I also had to remake the post that kind of holds up the whole electronics unit because it was printed in a poor orientation, so redoing the heat inserts. Before anyone says anything, those are temporary. Here it is, semi-installed. It'll look like that, I swear, right? It's basically the same. So that means it's time for a test drive. And look, you're seeing about 40 kilometers an hour. Oh. This is when I kind of roughly started to realize that electrical noise is kind of totally a thing here. And you can't just use whatever you find on the shelf. So it was fine before on the test bench when I had a real short cable because there wasn't really any interference on the wiring. But it's kind of not possible to go 13,000 kilometers per hour in a Cummins. I mean, you could if you really want to, but... So you gotta go into your shop, go a couple shelves up to where you can find your shielded cable that you've been saving for years. Because that seems to fix it. Probably also helps to have a working motor, because for some reason the last one died. Not really sure why, but I feel like that's going to be a common issue. Okay, now I think I figured it out. Time to actually run the shielded cable. And maybe go for a second drive. Overall, I'm pretty happy with how it turned out. Sure, it's a bit jumpy, but that's likely due to me not grounding the shielding right away yet. It's a lot better than what it was, but it definitely needs to happen. It was a cheap, usable solution to get a speedometer in the use cases that my dad uses his truck for, which is just bombing around town. Now it has a little bit of limitations just because of the angle of the servo. This is because it's only able to operate between the speeds of 0 and 90 kilometers an hour due to the limitations of this specific servo model. If you are interested in doing a similar project, here's some just general notes. Definitely use high quality wiring. The shielding made a big difference even though it wasn't grounded. Test on the bench as much as you can and really consider that it's a prototype. Things will go wrong. And yeah, spend a bit more money on a higher quality servo so it's likely to last longer and so you can achieve the beyond 100 kilometers an hour or however your speedometer is laid out. If I was to do it again, and I might, I'd spend the time to design and manufacture a PCB dedicated for it. It can include the voltage step down, microcontroller, all in one, while still being a smaller footprint. It also allows you to use better connections like some small JSTs. Oh, and I guess I also install into the dash.